So let's say we have an object that's rolling off or being thrown off or jumping off or whatever the case may be, off the edge of a building or off the edge of a cliff, something that's higher than the base. And let's say it's going off completely horizontal. So it's not on a ramp, right? It's not on an incline going up like this as it's launched. It's just going straight off the edge horizontally like this. And let's say it's going at a speed of 10 meters per second. And let's say the height of this cliff or building or diving board or whatever happens to be is 12 meters. What's the path of this object? What's the shape of the path called that this object follows? Yeah, it's called a parabola, yeah. Some of you guys are going to be more familiar with that term than others. Those of you who have done it in math class are going to know exactly what we mean by a parabola. We talked on Friday a little bit about parabolas though, so all of you have some kind of insight now as to what a parabola is. This is the shape of the path. It ends up being a half a parabola, right? But we'd still call it a parabola. Now, let's say that we're trying to find how far from the base of this cliff that this object lands. Trying to find this distance right here. We know very well what to do for this question. We know that for this question, we have to break it up into X and Y components. Why do we got to do that? Who's got an answer for that? Why do we have to break it up into X and Y components? For the same reason we had to break this up into X and Y components, because there's things happening on both the X-axis and the Y-axis. Now, this question looks different than this question. These are all straight lines in this one. This is a parabola, but in the end, that doesn't matter. In the end, in both cases, we've got an object that is moving on both the X-axis and the Y-axis. It's moving not just this way or this way, but both. Does that make sense? Whenever we see that, we've got to break it up into X components and Y components. So let's erase this and go back to the question at hand here now. We break it up into X components and Y components. We deal with the X component and the Y component differently than we dealt with the X component and the Y component in those other questions, though. How do we deal with it here? Well, we write down an equation for both X and Y. Which equation am I always going to use for X? Always. On your assignment that's due later today, but also on your test on Thursday when you see a question like this. Hear what I said? When you see a question like this on your test on Thursday. What equation are you going to start off with there, Bruce? Good. Can anybody tell me how Bruce knows that you're going to use V is equal to delta D over delta T for the X component always? Yep. Good, excellent. The horizontal component is always constant velocity if we're neglecting air resistance, which we will always neglect air resistance. Why is that the case? Well, the speed of the object horizontally isn't going to change if there's no forces acting horizontally. And if there's no air resistance, there are no horizontal forces. There is a force acting here, right? What's it called? The force of gravity, but it's acting downwards, right? So it's not going to cause a horizontal change in velocity. It's going to cause a vertical change in velocity. That means for the Y component, we're going to use a group B equation. Now, there's 5 of them that you're allowed to use here. 5 of them that are completely valid for the Y component. Which one are we always going to try first? Good. VIT plus 1/2 AT squared. Now, remember, it's not the only thing that you can try, but it is what you should try first because it's the one that's going to almost always work for you. Got it? Listen, I told you on your assignment, I think it's question number 7 and number 8, you're going to start off like this. On your unit test, when you see a question like this, you're going to start off like this. And question number 1 on your final exam, you're going to start off writing down these 2 equations. I'm telling you right now, question number 1 on your final exam should start off like this because it's a projectile motion question. Now, what's the next thing you got to do? Well, now comes, in a sense, the easy part because you don't really have to have a strategy at this point. You just sub in numbers and see what comes out. Don't worry about getting what you're looking for. Hey, we're looking for how far the ball lands from the edge of the cliff. Don't worry about that. Don't panic about what you're looking for. Just plug in numbers and try to get something here. What do we have? Well, let's start with the x component. Do we know what v is for the x component? Yes, we do. Okay, it's launched horizontally at 10 meters per second here. So let's fill that in. Do we know what d is? Displacement. Do we know what displacement is? Jillian, do we know what the displacement is there? Negative 12, okay. Negative 12. Is that right, guys? Oh, she's so close. Well, it's not negative 12 for the x component, right? How far below where it starts does it end up? Negative 12, right? That would be the y displacement. How far does it go horizontally? That's what we're looking for, right? So we don't know what that is. We're going to leave that as an unknown. We don't know how long it's in the air for either, right? But we're not going to sweat that either. Listen, we weren't able to solve for anything. That's okay. That happens all the time. Not literally all the time, but it happens lots. That we end up having two unknowns there. That's okay. We got two equations. Let's go to the other one. See what happens here now. Jillian, do we know what the displacement is for the y component? Good. Negative 12 meters. Somebody else now. Do we know what the initial velocity is, Logan, for the y component? Good. It's moving at 10 meters per second, but that's not y component, right? That's the x component. Now, the x component velocity doesn't change, but the y component does. So 1/10 of a second after it's launched, the y velocity is not 0, but the initial y velocity is 0. We don't know what the time is, but we know that 0 times the time, whatever that happens to be, is what? 0. 1/2 of, what's the y component of the acceleration? The x component would be 0, right? Because there is no horizontal acceleration. Nick, what's the y component of the acceleration? Good. Negative 9.81. And then we multiply that by t squared. So usually what I do at this point is say, although I don't usually write this step down, I kind of just do it in one step here. I multiply 1/2 times negative 9.81. You get negative 4.905. It's just multiplying those two numbers together. And then I take the negative 4.905 to the other side by division, right? So 12 divided by 4.905. Does anybody have that? What is it? 2 point, that's t squared, right? Is equal to 2 point. Okay, let's go 4 or 5 decimal places. 4 is probably good there. T squared is equal to 2.4464. And then how is it that we're going to find t, Danny, now that we have t squared? Good. We're going to square root it. And does anybody have that? Yep. Keep going. 1.5641 seconds. Good. Listen, that's not what we were looking for. Right? We weren't looking for time. Does that matter? No. Is it wrong? No, I don't think it's wrong anyways. I think we have the right time here. Now that we have time, that makes what we are looking for easier to find. How are we going to finish this off, Beck? Yeah. So let's take that over there, right? Why is it, other Zach, why is it that we're allowed to move the time over between x and y components here? Yeah, good. Time's a scalar. Velocities, right? 10 and 0. We can't interchange those, but time we can because time's a scalar. All right, so we're going to say 10 is equal to delta d over the time of 1.5641. Now we're going to take the 1.5641 up to the top. Nicole, what are we going to do there? How are we going to take that up? Good. So it becomes d is equal to 10 times that. It becomes 15.641 meters. Or we're going to round that to how many digits, Emma? 2. So we're going to make it 16 meters. There you go. It ends up landing 16 meters from the edge of this cliff or building or whatever. We had a couple of homework questions over the weekend on this stuff. It was questions 1 and 2 on page 107. I'd like to go over I'd like to go over question number 2. Pick a number 2 because question number 1 is, except for the numbers, identical to the one we just did, right? If you can do the one we just did, then you can do this one. If you had trouble with that one over the weekend, go back and try it again after the question we've just gone over. Question number 2 is almost the same, except we're looking for a different variable. That's all. Let's try question number 2. It says, an arrow is fired horizontally with a speed of 25 from the top of a 150-meter tall cliff. We want to know the distance the arrow will drop in 2.5 seconds. So here's the cliff. Here's the arrow. And it's moving at 25 meters per second. We got a 150-meter high cliff. We want to know not how far it goes, but we want to know the distance that it falls. What are we looking for here? The y what? Yeah, the y displacement, yeah. We want to find the y displacement. Don't we have the y displacement? How many people made the y displacement 150 meters or neg 150? That's wrong. What relevance is the 150 meters? Where do we plug that in? We don't. Why not? Why do we not use the 150 meters here? Why is that, Rudiana, relevant to this question? Yeah, we're looking for how far it falls. We're told that it's 150 meters. Listen, if this cliff was 800 meters high, would that change how far the arrow's fallen in 2.5 seconds? No, right? As long as it hasn't hit the ground, then the arrow's going to fall the same distance in 2.5 seconds, regardless of whether the cliff is 150 meters high or whether it's 800 meters high. So I'm actually going to scratch that out there. I'm going to say that the arrow is going to end up here after 2.5 seconds, and we're looking for the y displacement like this. Does that make sense what I've done with my picture there? That's a tricky question, hey? That's nasty to throw it at you, to give you that number to, doesn't really matter. Remember I told you that little analogy with the blue car earlier in the year? The blue car phenomenon? It's exactly what we have here, right? The blue car is traveling down the road at this speed for this amount of time. What's the displacement? The color of the car was irrelevant, right? Now the height of this cliff is irrelevant too. All right, let's do what we do now. What comes next? Write down the numbers. Yeah, we got to write down some equations first under x and y components. So we're going to say v is equal to delta d over delta t. And for the y component, we're going to say vit plus 1/2 et squared. Just because this is a trickier question with that displacement that we were given doesn't mean that we change the basic strategy that we follow for this question. Bless you. Sub in our numbers. Do we know what v is for the x component? Emily, do we know what v is for the x component? Good, it's 25. So it hasn't changed a thing, right? 25 meters per second. Do we know what delta d is for the x component? Nope. Do we know what delta t is? Yeah, we do, don't we? 2.5 seconds. So delta d for the x component ends up being 25 times 2.5, which is going to be 62.5 meters. Is that my answer? What have I just found, Kelly? Right. Is that what I'm looking for? No, I'm looking for how far it goes vertically, right? All right. Maybe that helps me later on. Maybe it doesn't. Okay, well, let's do the y component since we haven't found what I'm looking for yet. Do we know what the y displacement is? That's what we're trying to find, isn't it? Do we know what vi is for the y component? What is it? 0, because it's launched horizontally. What's a? Negative 9.81. T is 2.5. We got to square that. Let's figure out what delta D is now. We do the math there. We get negative 30.6563 or negative 30. We're going to make that 3 digits, right? Negative 30.7 meters. That's our answer, isn't it? How far, the distance the arrow will drop in 2.5 seconds, isn't that 30.7 meters? Technically, distance is a positive value, right? Because it's a scalar. You make it negative, I'm going to accept that. The displacement is negative, the distance is positive. What relevance was the x component here? Did that help us at all? No, it actually didn't in this question, did it? Hey, I knew that when I started this question. I've done this question before. I knew it wasn't going to matter. My point with doing that is, listen, first time I did this question, I wouldn't have recognized probably that the x component doesn't matter either. My point is, it's okay if you don't spot that, right? It's okay if you don't notice the x component's not going to matter. Do it. Oh, it didn't matter. What just happened? I just used up 30 or 45 seconds of my life. And I know I'm never going to get it back, but I'm probably going to survive having lost that 30 or 45 seconds. Hey, don't sweat it. You did some extra work. No worries. You got an answer for the horizontal displacement. You're not looking for it, but that's okay. If you get extra stuff, that's okay. We good there? All right. You guys are okay with that, I think. What if I get a question, though, that is not launched horizontally like this, but rather is launched at an angle like this? Let's say that this ball was moving at 10 meters per second off the edge of a 12-meter high cliff. That's the question we did as our example a few minutes ago, right? Let's say this ball was launched at 10 meters per second from the ground, ends up back on the ground, but is launched at an angle of, let's say, let's pick a random angle, 30 degrees. We want to know how far both of them go. How far does this one go? How far does this one go? Well, we already solved this problem. That was our example a couple minutes ago, right? How do we do it? Well, we broke it up into x components and y components. We said v is equal to delta d over delta t for the x component, and we said d is equal to vit for the plus 1/2 at squared for the y component. And then we subbed in numbers, and we ended up getting a value for the x displacement, right? What do we do for this one? Same thing, right? We're going to say the x component is v is equal to delta d over delta t. And the y component is d is equal to vit plus 1/2 at squared. Now, I can live with, if I asked you what are you going to do first for this second question, I could live with a couple possible answers, actually. One is the answer that I just got. Okay, that's a good answer for what do I do first. Okay, the same thing as I did for the example question we did a few minutes ago. But there is one more thing that I could live with as well. Does anybody think they might know what I'm looking for here? What else do you see here that you already know that you're going to have to do right away? What do you see here? Is there anything that bothers you about this question? Kelly? I don't like funny angles. I got a funny angle of 30 degrees. So what do? You get rid of it with a triangle, right? Let's go over here off to the side. This is x, this is y, this is 30, and this is 10. Let's say cosine 30 degrees is equal to x over 10, and sine 30 degrees is equal to y over 10. Is this any different than what we were doing with our vector addition problems? Not at all. We got a funny angle. We got to get rid of it. Listen, next year you're going to do something called conservation of momentum, where maybe two cars are colliding like this at an intersection. Maybe two curling rocks are colliding like this at funny angles. You have to deal with it. The first thing you're going to do is say, I don't like funny angles. And you're going to do what we just did. Get rid of the funny angle. Now we sub in numbers. What's the x component of the velocity? 10? No. Remember what we said? Once you resolve that funny angle, it's gone. Like that initial one is gone. We got a y component here that's 5. We got an x component that's 8.66. Now that doesn't look like follows a parabola, but remember we're not tracing the path of the ball here. Okay, that little vector diagram that we just drew shows the initial velocity of the ball, not the path of the ball. What's the initial x component? 8.66. And the horizontal displacement, we don't know. The time, we don't know. What's the vertical displacement? Oh, this is a good one. What's the vertical displacement? Oh, we do know. Yes, we do know it. What's the vertical displacement? Where does this ball land vertically relative to where it started vertically? 0. The y displacement here is 0. It doesn't land above where it started. It doesn't land below where it started. In this question, it was -12, right? In this question, it's 0 because it lands on the ground. It lands at the same height that it started at. Does that make sense? Horizontally, it's not 0, but vertically it is. What's VI for the y component here? 0. 0? Oh, I almost got caught there myself. It's not 0. It was 0 over here because it was launched at 10 meters per second, right? Horizontally. Here it's launched at some funny angle. What's the initial y component here? 5, right? We just got rid of the funny angle and turned it into 8.66 and 5. The initial y component of the velocity is 5. And the time, we don't know. Well, it's looking a little bit ugly. Let's simplify this just a tiny bit here. Say 0 is equal to 5 times t, subtract 4.905 t squared. See what I did there with that? Jonah, where did I get the 4.905 there? Good, 1/2 of -9.81. Now, that's tough to rearrange to solve for t there. If delta d was not 0, you could not do this without the Pythagorean, without the quadratic equation, which a lot of you haven't even learned in math class. But the good news is VI is not 0, but delta d is 0. So this is still doable. Watch very carefully what I'm going to do, because this is tricky. Remember, I can do whatever I want, but I got to do it to every term. I'm going to divide every term by t. 0 divided by t, 5t divided by t, and -4.905 t squared divided by t. What's 0 divided by t? 0. What's 5t divided by t? 5, because t divided by t is 1, right? What's 4.905 t squared divided by t? T squared divided by t, one of the t's cancels there. Becomes 4.905 t. Right? Now it's looking better, isn't it? Now it's looking more manageable. Take the 5 over to the other side. I get -5 equals -4.905. Now I'm just going to do some division here. -5 divided by -4.905 gives me 1.01937. Which I can plug back into here. And multiply it by 8.66. And I get a displacement here of 8.83. Should be 2 digits though. So 8.8 meters. Is it the same as the last question we did? Not exactly. But is it almost the same? Yeah. when you take a look at both of these questions that are up on the board right now, the one we did as our example before, and then this one, what's similar about them? Just about everything. What's different about them? Three things are different. The x velocity is different. Okay? The x velocity in this problem is just whatever velocity you're given. In this one over here, it's a component of what you were given. What else is different? The y velocity. It was 0 in the first problem. In the second problem, it's a component of what you were given. Finally, what else is different about it? The y displacement. The y displacement was negative something. Now it's 0. So the x velocity was the given value. Now it's a component of the given value. The y velocity was 0. Now it's a component of the given value. And the y displacement was negative something. In this case, it would be negative 12. Now it's going to be 0. Those are the only three differences. So if you can do the first question, then you can do the second question if you recognize those three differences. All right? Make sense? What I would like you to do now, before you tackle the assignment question, because there is an assignment question that's just like this, except they ask one additional thing. Okay? I want you to just practice a little bit with question number 2 on page 109. Question number 2 on page 109. No, that's not the one. I'm not sure where the one I want is. Here's what I'm going to do then. I'm just going to create one for you. Let's create another angle. What do you want to go? No, I don't like that one. No, I don't like that one either. 36, no, I don't like that one. Let's go 60. Okay, 60 works for me. Okay, change it up a little bit. Usually we go 30, we'll go 60 this time, okay? And let's make the velocity of it 20 meters per second. Hey, by the way, does anybody want to make a prediction? If you wanted to maximize the range or how far it went, anybody want to make a prediction of what angle you'd throw it at or kick it at? 45, yeah, 45 would maximize it. If you go under 45, then you don't get enough hang time, right? The higher the angle, the more hang time you get, right? But if you go over 45, then it goes too straight up, so it doesn't go as far. To maximize the range, you'd go at 60 degrees. The question is, how far does it go? Okay, see what we can do with that. And then, after you finish this and maybe mastered this concept, then we'll let you do that question on your assignment. All right, time to take a look here. Hey, what's the first thing you're going to do here? You can go x and y components and write down the two equations. Okay, that works as an answer for what you're going to do first. But what else could you do first? Yeah, I draw a triangle, get rid of that funny angle because we don't like funny angles. So let's go off to the side here. Let's see, we got 20 meters per second, and an angle of 60 degrees. Okay, let's make this x component, and let's make this y component. Remember, we're not finding the x and y component of the motion of the object. We're finding the x and y component of the initial velocity of the object. The x component is going to be found by cosine. I think x equals 10 in this case, meters per second, not meters, but meters per second. And the y component is going to be the sine function. And I believe that one is 17.32. Yeah? All right, there's my off to the side a little bit there. I can replace this if I want with a x and a y. Here's a y that's 17.32 and an x that's 10. All right, net meters per second, right? Not meters, but meters per second. It's not how far the object is going, it's the initial velocity. All right, so now we do our x components and our y components. And for x, we always, Holly, say for the x component, what equation? Good, good. Delta d over delta t. And for the y component, we're always going to try, which one, Danny? Good. Doesn't mean it's always going to work for us, but that's always what we're going to try, because 99.9% of the time that's what's going to work for us. So let's sub in some numbers here. Do we know, Zach, do we know what V is for the x component here? Yes, good. And we don't know what the horizontal displacement is, and we don't know what the time is. So let's move back to the y component. Other Zach, do we know what delta d is for the y component? We do, actually. Where does it end vertically relative to where it started vertically? Zach, does it end above or below where it started? Yeah, the same. So what would delta d be? Right. Good. Liam, what's the initial velocity y component? How fast is it moving initially, up and down? Good. Yep, good. 17.32 meters per second. Times it by time, plus 1/2 of neg 9.81, times it by time squared. Now, what we're going to do here is divide everything by t, and we end up getting 0 is equal to 17.32 subtract 4.905 times t. Right, a t disappears from each term on the right-hand side. Negative 17.32, because we're taking that over by subtracting. 4.905 times t. What does t equal? 17 divided by 4.9. What is it? 3.53 seconds, which you're going to turn on and plug into here. So delta D ends up being 35.3 or 35 meters. You good there? Okay, follow-up question, which is like question 8B on your assignment. Follow-up question. What's the max height of this ball? Let's say I'm designing, let's say I'm an architect or an engineer and I'm part of the design team building a baseball stadium or a football stadium, but it's in Calgary, so it rains, it snows lots, right? Like playing baseball in October, who knows, maybe we get snow. Playing baseball in April or May, we get snow and rain like crazy. So we want to put a roof on it, but how high do we need to make this roof? So baseball doesn't hit the roof, right? What do? Well, we take a look, first of all, at the y component, right? If you're analyzing the max height, that's going to be the y component. Look, you want to find this? It's the y component. What are you actually solving for in the y component? What do you think it's going to be? Is it v or t or d or what is it? It's a displacement. Don't we already have the y displacement? Well, we have the y displacement for the whole trip, right? But we don't have the y displacement for that part of it. That's what we're trying to find, the displacement, right? Tell me what happens vertical. Horizontally, the velocity remains 10 meters per second, right, the whole time. Doesn't change horizontally. But vertically, what happens to that 17.32 as the ball goes up into the air? It slows down. So 17, 15, 12, 10, 5, 3, 2, 1. And when it reaches its max height, how fast is it moving vertically? 0. So let's say at max height, VF is 0 meters per second at max height. And let's say VF squared, let's write that so you can read it. VF squared is equal to VI squared plus 2AD. And we're going to just simply rearrange this to solve for delta D. We had a delta D for the Y component as 0, but that was for the whole trip, not when we were finding max height. Delta D now for max height is different because we're only looking at part of the trip now. We're going to take VI over by subtracting, and we're going to take A over by dividing. So clearly, this is not a baseball stadium design question because our initial velocity would be much higher for a hit baseball, right? But you can imagine how we would translate this into a baseball stadium design question if we made the initial velocity much higher, right? VF is 0. VI, what's VI? 17.32 because we're analyzing the Y component. Zero squared minus 17.32 squared over 2 times negative 9.81. Let's do that one on the calculator here together. 0 squared minus 17.32 squared. Let's press equals on that. And let's divide that by, use some brackets on the bottom, 2 times neg 9.81. And we end up getting 15.3, or should just be 15 meters, I guess. How high is this ball going to go at its max height? 15 meters. Remember what we said? Most times for the Y component, you're going to use this equation, right? Well, here's a situation where we didn't. We're still doing the Y component, but we're actually using a different equation for the Y component just because we're looking for something a little bit more unique than what we were before. Okay, the method in blue there is the general find pretty much anything method. This method in red is a method that's very specifically designed to find the max height and just the max height.